Fellow physics nerds. Today I decided to do a tutorial on classical mechanics, or more like an introduction to classical mechanics, otherwise known as the study of how things move. This course might also be entitled Analytical Mechanics. Uh, it just depends on the way you look at things, but in essence, we're looking at how things move. And if anything in this video or tutorial sounds like Chinese to you or a totally different language, make sure to catch up on my mathematical videos or tutorials on vector calculus. I will assume that you have a little bit of knowledge in differential equations and vector calculus for the rest of the video. Now, straight up concepts that you should know: space, where we describe our events to be. Space can hold a reference frame in which we can place objects and describe their position, or of which position can be described with a point P and with three components, x, y, z, or if you're in a two-dimensional axes, x and y, it can also be described as a vector, starting from the point of origin of your reference frame to your point P. To help you get a picture of this, here is my three-dimensional Cartesian coordinate system. Here's my x, here's my y, and here's my z. This is the, I guess, physical standard of how to measure your three-dimensional plane, not the mathematical. The mathematicians usually do it, the x and y are at the bottom like a sheet of paper, and then the x shoots up. I, however, just got used to this notation, so they're both the same thing, it's just a little bit of rotation. Anyhow, here is the point P, as I told you before, in space, in reference to a point of origin over here, x, y, and z, describing its position. And then here is its vector with x, y, and z, and then I, j, k as its unit vectors. Sorry, blanked out there. So the unit vector being this length, and this length. You know. Anyhow, moving on. We also need to refresh our memory on vector operators, or how to mathematically treat vectors. Over here, we have the first important one, or the sum of any two vectors, 3, 4 of any amount of vectors. If you have r and s, which both are vectors, you sum their x component, their y components, and their z components. This should look familiar if you've ever had to do like the sum of the forces and things like that. That is the most apparent or the most common typical way of seeing this operator at work in earlier physics courses. But then again, this should be review. This should not be a new topic for you. Already saw the sum vector operator. Now we need to refresh our memory on the dot product, and hopefully that doesn't stay at the top or whatever. There we go. Dot product. Let me delete that so I don't confuse you. So now we're going to see the dot product, or the scalar product of two vectors. And that, if you take a look over here, is again using the same vectors that we had previously, r and s. The dot product, noted as the dot, that's how, hence the name, is the magnitude of both vectors times the cosine of the angle between them. Sometimes, if we don't know the angle, we can also represent this by the sum of the multiplication of each component, or otherwise, like, I don't know, you just basically take the x components, multiply them together, add them by the product. Add them to the product of the y components and add them to the product of the z components. It's a little bit tedious, but always remember that the dot product of two vectors equals a scalar. So you should get a number. You should not get a vector as a resulting answer. If you do, then you probably did something wrong. Cross product, and that is simply the determinant of the vector components organized thusly. Again, this should be a review. You should already know what a determinant is. If you don't, look it up. It's really quite simple. You arrange your unit vectors up top. You place the vector components thusly. The component on the left goes in the middle, and the component on the right goes at the very bottom. And you do like a little crisscross action. You'll understand. Just look it up if you don't know. But again, this should be a review for you, not anything new. Classically, let me write that down for you. Classically, time t was a universal parameter. Everyone saw the same time change over the same time lapse. However, because of relativity, we now know that is false. However, since every single velocity that we will study is much smaller than the speed of light, we can still assume that all of our observers witness the same time, if you want to say that, if I'm allowed to say that. But anyway, everyone will have synchronized clocks, and everyone will not disagree in simultaneity for the purpose of the study of classical mechanics. Like I said, for velocities much slower than the speed of light c, and for the scale of us humans, I mean, we're going to be looking at objects in the kilograms, not necessarily objects in the atomic size. So we can neglect the changes in time. And for us, time is universal. Just want to get that out of the way so we can get into reference frames. So finally, something kind of cool. So reference frame. A reference frame is, like I said, the coordinate system set up in space. That is where you will refer to a point of origin. That is from where position is measured, and also time and velocity is relative to a reference frame that can be stationary or inertial. I will abbreviate reference frame, that's RF, or inertial, which means that the laws of inertia hold true. And for our other type of reference frames,
it's 10 o'clock.
Sorry, that was my clock. Non-inertial reference frames are reference frames that are accelerating. So the laws of inertia are hold different forms, I guess you can say, hold different forms. So you might be wondering, what is a different form? What is the law of inertia? That is what we're going to get to next. The law of inertia is one of 3 Newton laws, or laws of Newton, I guess. And the law of inertia is the second one, but let's go in order. So Newton's laws of motion. The first is the law, oh, never mind, I stand corrected. The first one is the law of inertia. And that is, in the absence of forces, an object's velocity remains constant. Let's go to the second one. Second is known as force equals ma, and then the third law of motion is for every force there is an equal and opposite force. So equal and opposite, F equals ma, and first one, law of inertia. And moving on from there,